Okay, wait a minute. You gotta get moving slow. It's ooh, a little bit slow, but it won't affect us that much. Okay. It'll take a minute for everything to launch here. You know, let's see. Let me go back. Why did the others not launch? Oh, they are. They're. It's just taking a minute. Okay. Okay. So we rolled through all this. Oh, and it saved all my marks. So I'll come back and sweep through and work stuff, but I wanted to kind of get into the projectile stuff and work a few problems today. There's MATLAB finally. In through this, doing here, and ordinarily was, or in the book was S right up here. He's putting a vector. And so all he's doing, and it is changing the position from a scalar, which was just moving along the line, possibly moving through a plane or through 3D. And so this vector R can change, or is my R with the bar over the top. So I don't know how this book is published, but you know, in today's market, there's ways in which you can do a global replace on everything. You know, you could go back and do that. This book originated back in the 80s or something. So you go through this thing. You already know this. I mean, here's your particle path, and that the velocities are tangent to it, which is useful along the way for various things later on, as maybe not too far later on. Then what happens is if you start staring at the vector and move a little delta, and the vector sort of points back to where like a curvature point is. And he does that, although I tried to do it there, but he does a better job. Well, okay, maybe I thought he did more stuff than that, but maybe I'm wrong. I thought he had, maybe that's in the next section where he has two vectors, he lines them up, puts them tail to tail, and shows that it points back. But so you got a path. Think about it. You already know that F is equal to MA. You already know, and you're not supposed to yet, but you already do know that. So you know for this to change its path in turn, somebody has to push it that way. Pressure or something like that. If it's pushing it that way and the mass is not changing, well, the acceleration has to be exactly the same way. It's just scale. Sort of makes sense, you know, that it wouldn't go tangent to the path. That it possibly could go along. Part of it could go tangent to the path if you're increasing the speed, and then part of it is the change in direction. For example, you get out in the parking lot. I mean, I'm not suggesting you do this, but you start going around and around, and you go in a perfect circle. So as you're going in a perfect circle, usually you're just starting off with speed is equal to 0. So you're hitting the accelerator, and you're accelerating as you're going through your path. Have an acceleration that's going that way because you're pushing on the gas pedal, but you can feel yourself leaning or being pulled over to the side because you're changing direction. What's usually a tangential in a normal component, but we're not supposed to know that in the next section. So in fact, there are two parts to this. One is the change in speed, or the change in, you know, I'm going 30 miles an hour in a few seconds, I'm going 40, then 50. There's the concept of holding the wheel to the left or right, and you're just going around in circles. What does he do? He just breaks the R into components. Nothing new that you've ever seen before. There's the IJK vectors, base vectors. I do a little hat over them. You probably have seen them with or without. He's made them dark. If you notice, they're bold font, so they're supposed to be vectors. You go through, and what you find out is you get a subscript on here, where this is nothing more than that. Now, you should be used to dot notation, and that all that is, you know, in this particular case, dx dt can be written with a dot. So the dot is that it's the time derivative of that, whatever's under the dot. You know, for example, the y dot is equal to dy dt. So this is just a change in notation. There's a lot of that happens in here. There's a lot of that happens that you're not aware that he's actually doing that. So that's one of the things I'm going to try to touch on as we go through this thing, through a lot of this stuff. Oh, and I've been hacking around on this thing. So everything is fine. You get down here, you do a double dot, which is basically, I mean, this shouldn't be, you've seen the dot notation before. So, I mean, it's not anything, you know, new to you. You go down here, and he's already starting to give you, what is that called? His procedures. So here you have a particular case. So he's doing this. He basically setting, he's setting x is equal to 8p. Well, that's easy to take the derivative. It just becomes 8. Then what he's doing is pulling it along a path. So if you want to, well, I guess you have to. You take the 8 in there, squared over 10, and you can go in and do it. Now, there's another way to do it too. And let's see, does he do it that way? So if you're looking for the velocity and the y, by definition, that has to be that. But he could just as easily do this, dx dy. I'm sorry, dt. So you've already got this form from right here, and now you're just taking the derivative of y with respect to x, which that's pretty easy to do. I think it's just 2x. So it'll depend on where you're at. 2x over 10. Wait, yeah. So get in here, he does that. He's looking at this, then he starts breaking things down. But you have a couple of ways you can do those things. And so that's pretty much it. You know, in all of this section, he's going to have to give you the path here. So he's going to have to figure out some way of giving you the path. This, and if you've got the path, he's obviously got to give you x as a function of time somewhere. So short time function. If the plane is rising in a constant upward velocity of 10 meters per second, determine the magnitude of velocity and acceleration when it reaches an altitude of. So a constant upward movement, he's going to have something along those lines. He's going to have to fit. Oh, here it is. 10. If you grab the 10. And for some reason, okay, so at 100, the only way to get that to be 100 is for 10 seconds. So then he goes through this thing. So, and that's something you already know too. So all of this is, I mean, there's not a whole lot much to it, but this is where I wanted to get to, and luckily he broke it apart and dropped this right in there. So what happens on this, and this is a good picture of this. This is a picture taken where obviously the yellow ball is shoved to the right with a certain velocity. And I don't know if the difference between the first snapshot and the second are any different, but what you notice here, each one of these is the same distance. Well, except that last one, because there is no picture of the last one. So what that should give you the indication, if this is a strobe, then what happens to you is it looks to me like, and of course that's because you probably know this too, the X component for the velocity just is whatever you imparted on it. So this could be like the pinball thing, or somebody hit it with a bat or something. It starts going this direction. If you take it with a constant strobe, you'll notice it moves always the same distance to the right. Now, if that strobe, the delta T between that strobe happens that way, what you notice here is this. Every strobe, it's getting larger and larger distance. And this was part of the stuff that they started noticing. And this, if you look at the original ways they did experiments, it was kind of interesting. They had a marble, not a marble, maybe a bowling ball or something that rolled down a plane. And what they found is they started noticing if it took, 1 second to go this far, 2 seconds was twice as far, 4 seconds was 2 seconds was 2 squared. They noticed it was a squared component to it. Then they started backing it out. And that was before they knew all of this, F is equal to ma stuff. So you can find experiments that date way before Newton that talked about this. Is if you look at it, you end up with a constant acceleration caught in here. This is just minus g. So if you wanted to go through with this, I guess if I'm keep to my same sequence, I need to start a new page for every lecture. So if your acceleration in y is just minus g, the x is just nothing, then you can say, well, what's the velocity? If I have that and use the general relationship is equal to acceleration, but both of those are constant, is dv is equal to, you can pick some t naught and t, leaving the t as being a variable. And then you can say v naught, which v naught is the velocity at. On the left side, you just get v minus v naught. You just get a, which can be just pulled out of there. Now, and so what you'll get is v naught plus, now, back in the book, okay. So v is equal to v naught ACT, so I should have put a subscript of a c there. But that's a general form. If you go back to this, I have velocity, which I should have put a c right there so I could pull it out. AC is a constant, I can just pull it out and integrate. So I'm sitting here with this one, and what I'm going to do is I'm going to apply this to these two equations in a second. So I'm doing sort of a generalization here to a position. I'll use S now, but I'm going to swap it for X and Y in a second. So if I want to, I look at that, I do the same thing with V dp, and this time I'll do T naught. Now, legally, what you're supposed to do is you're supposed to have minus T naught. You notice in the book, they don't have that. So there's certain things in life you can control. In an experiment, you can definitely control when you hit the stopwatch. So it makes sense that if somebody's holding a marble up in the air and you say go, you hit the stopwatch then. That would be T is equal to 0 would be wherever you're at. It doesn't make sense for someone to say start the watch and then 2 seconds later to drop it. So you're controlling, that's easy to control. So does that sort of make sense? So you can easily set T0 equal to 0. You don't have to, but if you didn't do that, you'd have an extra term hanging around over here. So, so that's why they do that. Now, legally, you're not supposed to do that, but that's okay. And S, same setup. This time, you got to, and if you just say this is 0 and go with it, what you're going to end up with is an integration of V naught t dt from 0 to some time. That would just be V naught at, almost said x, but it's V naught t AC2. But then on this side, you ended up with S minus S naught, or you ended up with S is equal to S naught plus. If you stare at that a minute, you're assuming that acceleration is constant. You drop this down, it makes sense. But then you've got to carry out the integration. You end up with this equation out of it. Now, again, this is assuming that T naught is started, the clock starts when you started the experiment, so to speak. How you would want to do it any other way, but you could. So what he's doing here is he's calling it X, and in a minute he'll call the other one Y. S. But you could just as easily put X or Y there. Now, if you start comparing it to projectile motion, what you'll find out is, okay, so maybe first I should do the AX. So if I do AX, oops. Okay, so AX, yeah, good. I'll make a box around it and say, first I'll do the X motion. So if you're doing the X motion, that pretty much it's equal to 0. You look over here and you just get Vx, I'm copying that one straight across, is equal to Vx naught, and there's nothing there. Because the acceleration is, I mean, I could put rotary times time, and I'm getting it from, what happened to my, how do I make that stay on there? There we go. So I'm getting it from this equation right here. And so if I'm getting it from that equation, I just put in a constant in the x direction, 0. That doesn't get you anything, so it's just erase it. And then the next one I'm copying from is this one right down here. Then that's just, instead of S now, it's X is equal to X naught, Vx naught time, and there isn't an acceleration over here. So that's it. Is like we were noticing in the picture, the x direction in the x direction perpendicular to gravity, it's the same velocity all the time. The only exception to that is in the real world where there's drag on a body and it'll slow the thing down. So you're kind of stuck with that, but we're not in the real world yet. We'll get there one day. So yours might be 2-3 years and then you graduate, and you're in the real world, and you're thinking, oh no. Okay, I guess the real world's okay. So the thing here is the G. Now this is assuming all of his pictures, okay, X, and gravity goes the other way. So if you look at it, this is pretty much universally assumed, you know. So it's not necessarily me. I mean, so then you got Vy is equal to Vy naught. It's the same thing, but minus GT. So what happens is the marble, it starts speeding up. And so gravity is making it speed up. Now, you start, okay, so you do this in the La La world, which is the textbook world. That kind of says that if you jump out of an airplane, 30,000 feet, you're just going to keep speeding up till you're just going, maybe 2,000 miles per hour or something. That doesn't happen. The reason that doesn't happen is the air is slowing you down, so you reach like a terminal velocity, like 120 or something like that. So there again, in the real world, there's a drag that slows you down in a vacuum. So, and the thing is if you're going a short distance and you don't have much drag, it probably is a good approximation. So then you get naught t minus over 2. So I'm just, again, all I'm doing is copying this over, replacing the s with that. In the book, that's exactly the two equations, although in a weird way first, like this. And then it goes down, I guess, maybe the next page, or maybe the page after. Maybe it's the page after. Maybe it's not the page after. Okay, come on. I bet he does it right. No, he doesn't do it right off. Okay, well, does he write the D right there? Isn't it? Is that it? Well, interesting. I thought he put the minus G in there. Well, anyway, it doesn't matter. We'll work the problem. Let's work one. Okay, determine the speed at which the basketball must be thrown at an angle of 30 so that it makes it into the basket. So let's just do that one. I don't know. That might have been one I did. I'm trying to purge all memories, so I made those homework assignments, and now I forgot which one I did. Then that's all fine. It works good. Okay. This is one of the problems that's annoying to me. Okay. Okay, so there it is. It's in meters. First thing you got to be careful of is whatever your units, you got to put your G. It's either going to be this, or if it was in feet, 32.2, but it's not in feet. The first thing I realized is that I need the initial velocity out of that. He doesn't tell me, he wants to know VA, but if I want to write VA as a vector, how about, it's the initial velocity. I don't want to necessarily label it. I don't want to label it this. X plus J. So the initial velocity in the X, which is that direction, and the initial velocity in the Y, which is that direction. Now, luckily, he gives me this 30 degrees, so I can pull this out. And if you want to, I can draw it a little bigger. A VA, say, here. So this should be VA cosine 30. Should be VA sine 30. With is the initial velocity out of this thing at A is just VA and plus VA sine 30 J. That's okay, except now what I need to do is I need to start making use of my two equations. The X naught plus Vx naught. And see, here I go and I do Vx naught, and there I put V naught X. So if I flip those over, you'll have to forgive me. Sorry about that. Y is equal to Y naught this time, T minus, well, this time I know it's 9.81. 9.81 over 2 T squared is what happened. I also know that it goes 10 meters out there. So I also know it looks to me as though it's 1.5. Is that right? 1.5 and 1.5 is 3, right? So I know eventually this ball ends up at x equals to 10 to what? 1.5. So what should I do now? Any ideas? There's a couple ways to do this. Now, see, I don't want to self-impose on top of you. One of the things, let me take one approach, and then there's probably another one that you would be okay with, and that's you may go find the time. Me, I tend to, and then you would use the time in order to back stuff out. Me, I'm going to try something a little funny, and that is that if I look at these two, well, first of all, okay, let me address, okay, we addressed T naught. That was earlier in the derivation, that you can start the stopwatch whenever you want. You can also place the ruler wherever you want. And he's helped you here. The ruler here, and he placed the ruler here. Okay, so what is x naught? Y naught. Okay, but he put it, okay, he has the ground right here, but he put the ruler right at the basketball, right? So he placed both rulers. I mean, think of it as x being a ruler and a y being a ruler. You can put the base wherever you want, but he's put them right at the ball. So isn't that the same thing as saying this? Have to keep track of, but you have the freedom to move that wherever you want. In this problem, it's kind of beneficial to put it right there where the ball originated from. That being the case, what you did by doing that, a little bit of complexity there with is you end up with x equal to, and what I'm going to do is go ahead and copy the component of the velocity here, VA cosine. So what I did is I copied that. Does that make sense? But I removed that x naught because it doesn't count. The next thing I'll do this one. Y is equal to now VA sine of 30 times minus, I don't know what is, might as well, 9.81 divided by 2, 4.905. Is that right? I think that's right. With these two. Okay, again, it depends on what you want to do. Me, I would tend to say, I like to see an equation, one equation to deal with. If I'm seeing one equation, well, let me ask him what VA. One equation, one of the things I can do, let's see, how could I do that? There's 2 or 3 ways I could do it. But I can go into the first equation and do this. Okay, VA cosine. Make sure I copied this down right. I'm pulling that in, right? Did I do that right? And then I could take that and stick that in here and stick that in here. It's equal to, oh geez, VA sine of 30. And then, oh, I got VA cosine 30. Did I do that? Okay. Oh, then the X. And now, unfortunately, I can't get away without some of that over here. 4.905. Now I got to do T squared. Oh, yeah. X squared. VA squared. Cosine squared 30. Did I include it all? I don't know if I did or didn't. Now here's where, you'll probably stop right now and go to a calculator. I'm probably going to stop and go to a MATLAB. So if you don't mind, let me see if I can do that. And I'll do it, okay, so I'll do it this way. I don't know how much experience you had with MATLAB. Is anybody in that course right now? Have y'all had it yet? Oh, you took it last. You already took it. Okay. Okay. So let me see if I can fit both these on there. So on the top, right up here on the top right, you can see I got my X10. So I'm going to use it like that. I'm just going to set X is equal to 10, and I'm going to set Y is equal to 1.5. And then what I'm going to do is I'm going to say SYMS, symbolic variable, but VA, because that's the VA right there. Sometimes it takes a minute for it to do that. Okay, so now I'm going to type in something called EQ in, well, there's only one equation, so I'll just call it equation 1. What I'm going to do is I'm going to move the Y over to the other side. What I mean by that is I'm going to do this. I'm going to say, move the Y over here and say that. I mean, I know that looks weird, but I'm only doing that just to set up for MATLAB. So what I'll do is EQN is equal to minus Y, and Y is already determined, plus, now I could put the VA over the VA or just recognize they cancel and just do tangents, but I got to do tangent D. Did I write the thing? No, I did tangent F. 30 degrees minus 4.905 times, now I can just do X squared divided by, here, I'll do the cosine first. Cosine degree 30, but I got to square that. And now I got to square, what did I call it? VA. I got to square that. So what you find, okay, hang on. So it drops all that out. When you're doing symbolic, it'll try to turn everything into integers, so it's awful looking. If you want to know that number, you just copy it and paste it, and it'll tell you the actual number. Now, to me, I like, did I type that right? Equals 0. Equals is an assignment. Equals is it's just the syntax for the solve. It's telling it that that's an equation, and it uses the equal to look at the other side. So I could have messed it up and said equals to 3. I would have gotten a different answer. Did I do that? Anyway, we don't want to do it that way. So here's the thing. I've got 2 possible velocities. And see, look at that. Isn't that awful looking? But there are 2 ways I can do this. One is I can use that double, turn it into a number. Uh-oh. What have I done wrong? Did I type in the equation wrong? Where's my equation? What did I do wrong? X was 10, Y was 1.5. Check me out. What did I do wrong? Did I leave out the first X? Oh. Yeah. I sure did. Yep. Times X. How about, let's try that one. Let's try that one. Okay, that's a little bit better. So I get 2 answers. One is, that kind of makes sense going backwards, but that's as if the thing came across there and it's going that way. The other is going out there. Well, let's see. How about it? 12.37. That's probably good enough. So from this, you get VA equal to 12. Oops. 0.37. Now, I hate to do this, but let's see. How can I get my way to the back of the book real quick and get back? I know. Well, I tried that before and it won't do that, but I can record the page number. So it's on page 53. This is, okay, where's mine? So I'm on page 53 in problem, what was it? F1223. F1223. Can y'all remember that, the number? Okay, okay, so let's guess 730. Yeah, close. See if I can run back. Okay. Nope. How about that there? Nope. Okay. Gotta be back in here. Now, are they answering the questions? Oh, they split the F's away from the, okay. I'm close. I'm getting closer. Okay. So see what he did. He ended up going in and finding out what that was. I got 12. What did I get? Yeah, 3.7. So we're close enough together. But he did. I mean, that's okay. It's okay to do that, to have that time, and then you have to solve both of them. So they have to reach that same spot at that same time. So to me, I'm okay doing it either way, but to me, there's a reason I like to take the X if possible and put it in the Y, because then I get one equation and I can just solve it out of that. Either way is okay. So let's see about another one, the book. Okay, now I think I'm on page 53. Huh. Yeah. So we did that one. Now, okay, and then we could do this one, although we got enough time to do that one. It's not that bad. That one's actually, this one's a little bit, that one should go quick. Okay, let's try to see if I can get it. Okay. If it doesn't, you know what I'll do? Okay. Oh, okay. Projectile fired with an initial velocity of 150. If it's 150, okay, 150 divided by 5 is what? 30? Is that right? So that means 30 times 4 means that thing is coming out at 150, but 120 is going this way, and what's 3 times it? 90 is going up. Does that make sense? So now he says the projectile determine the range when it struck the ground. So it looks to me like I need to know y is equal to, notice he puts the coordinate system right at the original. So if you do that, x naught is equal to y naught, and you really always want this to be 0. Yeah, so your y should be equal to minus 150, but it's also, let's see, dy naught, which I know what that is, t minus, what is the units? Okay, 9.81 over 2 t squared. So I know what that is. That's 90. So now I'm just solving for this. So let me just, to make it quick, let's just make use of MATLAB again. Okay, so what I'll do is clear, and then I'll do SYMST, and then I'll just go in and say equation equal minus 150. Whoop, wait a minute. Did I forget my y? Oh, well, okay, so as far as the wait. So I was using the equation from here over. Am I okay? Am I legal? 150. Well, it's 150 because it wasn't negative 150, but now I'm putting it all on one side of the equation. So what I'm doing, here's what I'm setting up, is I'm setting up the equation that's supposed to be q is equal to 0, but it's equal to 150 plus 90t minus 9.81 over 2t squared. So what I'm doing is I'm wanting this to be 0. Now I could write this equation and say that equals to minus 150. If that makes better sense, I could do that. Let's try that. Solve, and now I'll just write the equation. Minus 150 is the same as 90 times t minus 9.81 divided by 2 times t squared. Okay, obviously I get two answers. Supposed to, should. One of them will be minus 1 whatever, and the other one will be 19. Do I want to just say time is equal to 20? I don't know. I better not. 8864. So if I've got that, then I've just got x is equal to x naught vx naught t. I'll just take that in, and the vx naught was 120 times 19.8864, or x, the range should be equal to, I don't know here, I'm going to do something like this, 120. And so the range should be, oh geez, 2,386, 86, something like that. Let's see, I'm getting pretty hungry. So let's check this out real quick. What we were at? I don't know. Gosh, I don't. Were we? Oh, you guys remember better than I do. Ooh, I'm close. Wait a minute. What was the problem number we just did? 26. Uh-oh. No, that's 24. Did it? Okay, 239 kilometers. So that's about what I got. 2386. Good enough. Let's go eat.